Okay, let's start our lecture today. Now today we continue our discussion on assembly language by talking about the memory address space, okay, and also the data representation in the assembly language. Now basically, when we talk about the memory address in computer, now we are going to describe how we can access the data in a more efficient and more effective way so that we can speed up our process. Now you can imagine if we can only using a few clock cycle to access the data, that means the whole instruction time, the execution time will be reduced. As a result, your program can be speed up. Okay, now here we have the objectives of this lecture. Firstly, we are going to give you the concept about the address and also the data. Actually, more or less, we have given the concept about address and data before. And then we are going to talk about different addressing mode we found in the assembly language. And finally, we are going to describe to you the data representation of the assembly language. Now in this data representation, we mainly focus on the integer and floating point number representation in computer. Okay. Now let me first give you the idea about what is an address and what is data. Now basically the diagram, so at the bottom you can see the relationship between the address and the data. Okay. Now actually the address means how we can find the memory. Okay. Therefore it should contain a certain number or a certain number. For example, from 0 to 1000, then it becomes the address. It looks like a street. Okay, for a building, it has an address to identify where the location of the building. And similarly, for the data, that means it is the size for storage, so that after you found the building, you can describe the size of the room inside the building, and it can classify or represent the data stored into the memory. Now therefore you can see, now we have a definition about the memory address. It is the position of the memory data that can be accessed by the processor. And here you can see that normally the address can be specified in terms of a multiple of 8 bits. Therefore, you can the single digit for the address corresponding to 8 bits. Okay, and the multiple you could have 16 bits, 32 bits, or even 64 bits. And normally it can be represented using the hexadecimal number. Okay, for example, you have 1282. Now the reason behind why we using hexadecimal number, because it can easily convert into a binary number. For example, 1282, it will become 001, 0010, 1010, and 0010. Okay, and actually you divide or you convert each hexadecimal digit into the corresponding binary number, then it forms a binary number easily. And they show the position of the data. Now, on the other hand, for the data, it refers to the space for storing the code or values that can be processed by the processor. just like the example given to you, you can see that inside the memory, the size can be 8 bits, so that the address 725 store 55, it is a hexadecimal number, or it can store 2 in the memory. Now here we show to you the general organization about the memory. Now in the picture you can see that normally a memory can be addressed by a different number. For example, you can see the lower number, the lower memory address starting from 000, and the higher memory address, for example, we put down FFFF. It shows you a 16-bit address. And the memory mainly stores the instructions and data, and they are storing in a continuous way. Therefore, later we have a term so-called the locality of reference. It refers that the code and the data are storing in a continuous way, so that the next instruction is highly relating to the current instruction. And this continuous memory, we will call it a segment. Therefore, inside the memory, you can see we have many segments. For example, the stat segment. Now, it is a memory mainly used for store the address. Okay. Now, remember last time we told you that when you have a subroutine call, the returning address will be storing inside the stat memory. Okay. And then we have the other segments, for example, BSS segment. Now it specifies the uninitialized data, and actually the full name of BSS means block started by symbol. Okay. BSS, that means the data inside the segment are uninitialized, and normally we will put down some 0 for this uninitialized data. And we have the data segment. It mainly stores the data for the program, and the text segment, it refers that it stores the instruction or code. Okay. And at the bottom of the memory, you can find we have an operating system kernel. That means the OS, for example, Windows, Linux, etc. And they provide some system program for the computer. Okay. Now, therefore, because nearly all of our memory store the data and program in a continuous way, therefore we invent or generate many different addressing modes in order to access the code and data efficiently. Okay, and also by using the virtual addressing schemes such as paging and segmentation, we can implement the multitask features into the computer system, because now if we can classify this is the code, this is the data, we can swap out the code, swap out the data to the hard disk. And the memory vacancy can be used by the other program in order to achieve the multitasking in a computer system. And actually, by doing this, we should create the virtual memory in virtual addressing scheme so that we can swap in or swap out the segments. Okay. Now later we will describe more details when we talk about the memory on the virtual addressing schemes. Now for the addressing modes, here you can see we have many different types. Now we only describe the general addressing modes here without stick on any processor. Okay, therefore you may see that for any of our processor, they can employ these 7 addressing mode. Okay, including immediate addressing mode, direct addressing mode, indirect addressing mode, register addressing mode, register indirect addressing mode, displacement or index addressing mode, and finally we have the stack addressing mode. And we will describe each of the addressing mode one by one. Okay. Now firstly, we have the simplest addressing mode. It is the immediate addressing. Actually, now for any of the instruction, normally it can divide into 2 parts. The first part, it is the opcode. Okay. The second part is the operand. Okay. Now for different addressing mode, basically it mainly change the values or contents inside the operand. For immediate addressing mode, that means the operand in the instruction containing an actual value. Okay. For example, if you perform add 5, so 5 it is an immediate value and it will add to the content of the accumulator register. Okay. For example, you may after execute this instruction, you have AX equal to AX plus 5. Okay, AX refer to the accumulator and 5 is the operand. Okay, now for using the immediate addressing mode, it should be the fastest because you do not refer any memory in order to fetch data, so it is very fast, but it has limited range because the size of the operand is not too large. For example, you may specify 16 bits in the operand. That means you can add a value up to 2 to the power 16. If you have a larger value, then you cannot using the immediate addressing mode. On next page, we show you a diagram to show you the immediate addressing diagram. Here we have the operand. It indicates the values of the instruction or the data it is going to process by the processor. Now the next one, we have the direct addressing. Now here you can see that for the operand, it shows you a memory address. Okay. Now therefore, for the instruction add A actually refers to an address. And therefore, when execute this instruction, the processor will looking at the content storing into the memory address A and then add to the accumulator. Okay. So for using this addressing, the direct addressing, you have a single memory reference. Okay. And still it should be fast because you do not require any addition on the calculation of the effective address, because later you may see that we have the other approach, the other addressing mode that require our calculations on effective address. Okay, but still we have the limited address space because we call that the operand bit field is not too large. For example, you may have 16 bits only. That means you can only have access the memory address up to 2 to the power 16 again. Okay. Now, on next page, we show you the diagram about the direct addressing. You can see that here in the instruction we have the address, and when the instruction is going to be executed, this address will be used to fetch the data from the memory. Therefore, we say that we have a single memory fetch in this instruction. Now the next one, we have the indirect addressing. Now we can extend the direct addressing further. We call that for the address A is sold to the operand. How about if we specify another address in in A, so that this B will further access in order to collect the data or fetch the data. Therefore, for the indirect addressing, you can find that the representation is we use a bracket to show the address storing in A. It is not a data, but the processor required to further fetch the data for the content of A. And actually, it is the concept of a pointer. You further point to the other data by using the address storing inside the first address. Okay. Now, for example, in here we have the instruction add A. That means the processor will looking for the address A, and then it will obtain another pointer, another address, and this address will be the content locating at this address will be fetched to perform the actual addition. On next page, on next page we will show you a diagram about the indirect addressing. Now here we describe why we apply the indirect addressing, because we should have large space, because now originally this 16 bit it may occupy 16 this A can occupy 16 bits only, but if you refer to another memory location which we can talking about, it occupy 32 bits. That means it can cover a larger memory space. So the calculation can be specified by 2 to the power n, where n is your word length. If n is 32 bits, that means you can access the memory address up to 2 to the power 32. Okay. Now we can apply the concept further, that you have multiple or nested or cascaded indirect addressing. For example, we have 3 brackets here. That means you are using A, access B. For the content inside B, it is not a real data. It further access C and further access D, for example. And by using this approach, you can see that actually you can access unlimited memory address. However, the speed will become slower. Okay, because you have multiple memory access. Okay, that means it becomes a trade-off when you apply this multiple indirect addressing. Now on next page, now we show you the diagram, and you can see that in the instruction, the address A, it is not a real data. It only shows to you an address. and the processor needed to find the address stored inside the memory accessed by A, and then it will further fetch the data from the address B to obtain the data. You can see we have two memory access for the indirect addressing. Now, in order to reduce the memory access, because you may consider that in the program execution, the memory access is a slowing down reason for the program. Therefore, in order to speed up the instruction execution, now you may using the register addressing, so that the operand refer in the instruction, it is a register address. Now for the register, now later we will describe to you that in the memory hierarchy, the register, it is the farthest memory in the computer system. And then the cache memory, and then the main memory. Now therefore, by putting all of your data in the register, it should be a good idea, because it should speed up your execution. However, in the computer system, we have only limited number of registers that we can use. Therefore, if your calculation involves too many register address, you will become lack of register to be used. Now, by using the register addressing, you should have shorter instruction, because the register address should be smaller. For example, if your computer containing, say for example, 8 register, that means you have only 3 bits to specify the register address. Okay, and it when, as I said, when the instruction using register addressing, it should speed up, because low memory access. Okay, it will result a very fast execution, but we have just described it has limited address space. Okay, now therefore, like in some of the computer design, it may increase the number of registers, such as a design type so-called the RISC computer, reduced instruction set computer. It has more registers can be used in the computer system, say around 256. Okay, when compared with the SEHS3317, you may have only 16 registers to can be used. You can see that for the RISC architecture, it has more register can be used, and for multiple register can improve the performance, because actually when you design your assembly language or even the compiler, you can use the register addressing as far as you could in order to speed up your program, and you can instruct your compiler to write the data into the register. For example, in C program, you can using the following statement: register integer A. That means you will create a variable that store in the register memory. Okay. Now actually, the accessing method look like the direct addressing. Okay, but it does not have the memory access, the data can be obtained in the register. Now here we show you the diagram. You can see the diagram is more or less like the direct addressing, but here instead of having the memory, we have the register here, and we have speed up the program execution if you are using the register addressing. Now we have the indirect addressing. Now how can we improve the performance? And you can easily think about if we can replace one of the memory access in the indirect addressing by register addressing, then we can speed up the performance. So we have the register indirect addressing. Okay, it looks like the indirect addressing, but this time instead of putting a banker A here, we put a register address here, so that the processor will first look at the register and then looking for the memory address. Say for example, if the register store a B inside the register, then the computer will use the address B to find the data in the memory. Okay, therefore now the operand in the memory cell actually pointed by the contents of the register R instead of the memory location used in the indirect addressing. And again, the advantage for using the register indirect addressing is that it can enlarge the address space up to 2 to the power n. But the performance should be better because we have fewer memory access. Now on next page, we show you the diagram to show you for the register indirect addressing. You can see in this diagram, in the instruction we have the register address R. Therefore, when execute, the processor will using this R to find the address stored inside the register. For example, we store B in here, and this B will be used to fetch the data for processing. Therefore, we have only one memory access. Okay. Therefore, the performance should be better than the indirect addressing. Okay. Now the next one, we have the displacement addressing. Now for using this addressing, we needed to have a calculation for the effective address. Okay, EA stands for effective address, and actually the direct addressing look like the immediate address. Direct addressing, where we have the opcode and also the address. But instead of directly access the operand A as the memory address, we use this A added to a displacement stored into the R. Okay, so we can extend by using this approach. We can extend the memory access space. Okay, for example, originally you may have only 16 bits for the address, but now together with the value stored in the register, normally it may be 32 bits. Then the effective address, you may consider it become a 32-bit address, and that means it can access larger memory. Okay, and here now the two values specified to you is that the A is the base value, and R it is the register address that hold the displacements. Okay, and then you can using this approach to access the data. And actually, now you may consider that if you are going to continuously access some memory content, you can update the values inside the register so that starting from 0, then you fetch the data, and then you add 1 to the register, it will access the next data. Okay. Therefore, by using this approach, it is benefit for the continuous access of data. Okay. Now here, this diagram will show you the displacement addressing mode. You can see that the operand is divided into two halves. For the register, it shows you a pointer and the address A. They are going to perform an addition before it access to the correct data in the memory. Okay. Therefore, by using this approach, we say that it can access a larger addressing space, but the problem is that we have one addition in order to create the effective address, and somehow it may slow down the execution time. Now another addressing mode, we have the relative addressing. It is similar to the displacement addressing. And instead of using a register to store the base, we use the program counter directly. Okay. Now therefore, the addressing mode we use here is the program counter added to A, the content of program counter added to A, and it creates a new address. And normally, you may consider that it it look like using a jump instruction to jump to another location of the program. Okay, and by using this approach, you may say that it does not require to address the register. Okay, but it addresses the program counter. Okay, and now normally we may consider that for the assembler using the one pass that we described to you last time, one pass assembler, it may using this approach because during the one pass assembler, the label address may not be known in advance, and we needed to update the address by using the relative addressing in order to find the correct jumping instruction. Okay, and using this approach, just like the displacement addressing, it is good for the locality of reference. Locality of reference means that all the data or code usually form a segment. The data are storing in a continuous way. Therefore, using the relative addressing, we can speed up the data access for your program. And also, you may consider that to using this approach for the cache memory. Because later we will describe the cache memory, it is the second farthest speed of memory, so that when operate, basically, we found that the memory segments will be copied into the cache memory when one of the data inside the segment is accessed. And therefore, by using this approach, many of our data to be accessed will be locating in the cache memory. Therefore, the relative addressing should be a good addressing mode to access the cache memory because the cache memory is fast. Now the next addressing mode, we have the base register addressing. Okay, again we divide the operand into two fields, or we may specify one field only, where A store the displacement or address. We have a out to hold the pointer to be the base address, and this out can be explicit or implicit inside the addressing mode. For example, if you are using the base register addressing, we can specify the value of A only. When we access the data, this A will be picked up, and the computer will automatically looking at the base register to find the value B, and we add A and B to create the effective address. Okay, therefore the base register is need not to be put into the instruction. And by using this approach, you can see that the address specified in the instruction become longer. Okay, because we do not needed to save the bit for the base register. For example, in the 80xx6 system, the register BX, it is using as the segment register, so that it can be omitted in the instruction whenever you be using the base register addressing. Now the next one, we have the index addressing, and actually it looks like the displacement addressing, but we specify the displacement directly in the instruction, so that you can see every time when we compute the effective address, we just put A plus R. Okay, so the diagram shown to you may be like that. For the instruction, we have the opcode, we have A and R, and for the base addressing mode or index addressing mode, we specify R as the displacement and A as our base. Okay, now but for the displacement addressing, we reverse the position, where A become our base and R will become our displacement. Okay, it depends on how you describe which one is the base, which one is the address. Okay, and it is this addressing, it is good for the accessing arrays. For example, when you perform R++, you can just update the R. Okay, that means update the displacement, and then you can easily access the position, different position in the memory. Now, or you may have more complicated addressing mode because you have some combinations for the addressing. For example, you may have the post-index addressing, where A and R are not the actual values, and they corresponding to the register address and also the memory address. When using this approach, now you can draw a picture to describe the opcode R and A, and here we use R for the register to looking for the data. For example, we store C here, and A, we have the memory access. For the address A, we have the another address D, and the effective address is computing by the addition of C plus D. Okay. Therefore, we have the post-index addressing. We have two separate addresses storing in the register and also the memory. Now, on the other hand, we have another combination addressing mode. It is the p-index addressing mode, where we access the content of R first and then add to A, and the whole result is another address to be fetched in the memory. Therefore, for using this approach, you can see that the picture look like here again we have operands R and A. We first access the register to see another data stored in the memory register C. This C will be added to A. Okay, and then the corresponding address become A plus C, and this address will use to access the memory, and this contains the actual data. Okay. Now, therefore, by understanding the different addressing mode, you can see that we can generate different memory accessing scheme in order to access the data. Okay. Now, therefore, when different memory addressing mode have different advantage, therefore, in your design of the assembly language, you could think about what is the purpose of your memory access in order to choose the best addressing scheme for your program. Now, lastly, we have the stack addressing. The stack addressing, now for the stack memory, as I told you last time, it is a last in, first out approach. Therefore, to using the fetch memory, for example, this is our stack memory. We have a pointer always point to the highest address of the stack memory. When we issue the push instruction, we will decrease the address in order to save the data into the stack memory. For example, after the push instruction, it will save the data into the stack memory 12, and the stack pointer will be updated to FFFE minus by 1, so that the next data will be pushed further into the memory. Okay. For example, if you have another push, you may have update the pointer FFFD. Okay. Every time the stack pointer will be minus 1, and when you pop the data, okay, that means you are going to retrieve the data from the stack memory. The memory access will decrease by 1. Therefore, if you issue the pop command, the stack memory will give out 34, and the stack pointer will return to FFFE. Okay. Now, here we have the stack addressing. Now, last time we showed you that especially if your instruction does not contain any operands, you may using the stack address. You may push first 2 data into the stack memory, and after you execute add, then it will automatically pop the top two items from the stack memory and then add the result. Okay. Therefore, sometimes you may use the stack memory to perform the operation. But we described to you that the stack memory mainly used as the address memory. It mainly stores the address. Okay. Now here we have a revision about the instruction formats that we have already told you. Actually, for the instruction, it mainly divided into two parts: the opcode and also the operands. Okay, and it specifies the number of bits for opcode and operand. For example, for a 16-bit instruction, it may specify 6 bits as the opcode and 10 bits as the operand. For 6 bits, that means it can support up to 2 to the power 6 different instructions for the CPU. For the 10-bit operand, that means in an immediate addressing, you can process a data up to 2 to the power 10. Okay, it is around 1024. And the operand can be implicit or explicit stored in the instruction. If it is implicit, that means it will automatically access the specific register to obtain the data. Okay. If it is explicit stored in the instruction, that means you are going to using different addressing mode to access the register or the memory. And normally, for one instruction, it will have different formats because it supports different addressing mode. For example, you can support an instruction move AX BX, that means you perform register addressing, or you can perform move direct addressing. You specify the register direct addressing. It is going to store a 5 into an AX, which is a pointer to the memory access. Okay. Now, therefore, both of the instructions using the same instruction name. Okay, but they perform different addressing mode. Now here we have a summary about all of our addressing mode. Actually, we have described to you each of them. Okay, or you may have the combination between these addressing modes in order to perform your instruction. Okay, now here we are going to give you an example, but by explaining the addressing mode for the x86 computer system. Now, x86 basically it is invented by Intel, and nowadays this CPU is popular used in our laptop or desktop computer, i7, i5, i3. I think you should hear this name in your computer. Okay. Now for the x86, using the segment approach to classify the memory type, and it has 6 segments: code segment, data segment, extended data segment. Again, F and G stand for further extent of the data segment, and SS stand for the stack segment. Okay, now that means it uses different memory to store the program code and also the data. Now for each register, it is storing the information about the segments. For example, in the code segment, it stores the base address. It shows you the limits, so that's how large of your segments. It also has the access rights in order to protect the segments. Okay, for example, if your code segment it is used by the operating system only, then this segment will not be used by the user. And this base address basically used to compute the effective address. And in your program, with different addressing mode, it will calculate using this diagram. Okay. Again, we have the base register to show you the starting address of your memory to fetch the data. The index address, that means the pointer. The relationship of base and index is look like the base point to the start of the address space, and the index is specified by the pointer or the number of the address that reference to the base. Okay, and this index register can has a multiplier. You have 1, 2, 4, 8. It depends on the size of your address, because if you're writing a program that using a linear single address, that means 8 bit, then the multiplier is 1. If your address is using a word as the basic unit, then you may use 16 bits. Then you may have the multiplier of 2. Okay. Now together you may add a displacement so that you can shift the memory to further location. Okay. Then it all of them adding together to calculate the effective address. Together with the base address given by the segment, then you have the linear address that can be accessed to the main memory. Okay. Now, and here the displacement, you can consider that you may consider we have a jump of the instruction to jump into another location into the memory. Then you may using the displacement register in order to calculate the effective address. Now here we show you a diagram about the SEHS3317 processor register. You can see that in the 32-bit mode, you have general register for 8 only, where they are 32-bit. Okay, the segment register we have 6. That means we showed to you before. We have the facts. It shows you the condition and status about the CPU. And we have 1 instruction pointer. Okay, in order, this is the index base. Basically, it is used as the index. For the 64-bit mode, the architecture is similar, but we have updated the number of general register, and also we update the length of the fact register and also the instruction pointer. For the floating point unit that we will describe later, you can see that it can support it has 8 registers, and it can has a length equal to 80 bits. It has the control and status register, which is separate indicate the condition of the CPU. It has the test fed, which is a very old register used in the SEHS3317 floating point unit coprocessor. We found in 30 years ago, but nowadays we don't use the coprocessor. At that time, we may using the tag register to show whether the floating point number is valid or not. It may have a normal number, or a 0, or NaN. NaN means infinity. Again, for the floating point unit, you have instruction pointer and data pointer, okay, in order to help the processor to compute the arithmetics for the floating point numbers. Okay. Now to the right hand side, we show you some the register RAM for the 8086. You can see we have AX to DX, they are the general purpose register. We have the pointer and index specify the step pointer, base pointer, they are the base address register. And SI and DI, they are the index register. We have the segment register specified by CS, DS, SS, and ES, and we have the FAT. And similar configuration can be seen in the 386 and Pentium 4 architecture. But now the general purpose register and index pointer register are extended to 32 bits. Okay. Now I think let us take a short break